Introduction. The purpose of this lab is to implement Newton's law of universal gravitation in computational models and use it to calculate unknown variables. Models and fundamental physics principles used. A computational model of a star orbiting a black hole in which the star is the system and the black hole is the surroundings, and a computational model of a spaceship orbiting a planet and its moon with the spaceship being the system and the planet and the moon being the surroundings. Preview of results. The mass of the black hole is about 1.2 times 10 to the 24th kilograms, and if the ship is launched from the moon with an initial velocity of negative 4850 in the x direction and positive 43747 in the y direction meters per second, the ship's path will be affected by both the gravity of the moon and the planet. The main physics ideas used were Newton's law of universal gravitation, parallel and perpendicular forces, and Newton's second law. Newton's law of universal gravitation was used as obviously, all these celestial bodies, the only force acting upon them is the force of gravity. Parallel and perpendicular forces were used because orbit is a curving motion problem, so you can convert the gravity force into perpendicular force to solve some more variables. And Newton's second law was used to take the net force acting on each of the celestial bodies and put them in terms of acceleration so they could be plugged into the velocity update formula and in turn later the position update formula. The initial conditions for part 1 is, the gravitational constant is 6.7 times 10 to the negative 11th. The mass of the star was 2 times 10 to the 30th. Each interval iteration was 60 times 60 times 24. Initial time was 0. The initial conditions for part 2 was the gravitational constant once again at 6.7 times 10 to the negative 11th. The mass of the planet was 8 times 10 to the 27th. The mass of the moon was 6 times 10 to the 25th. The mass of the ship was 7 times 10 to the 12th. Delta T is 60 and time starts at 0. Code for part 1. As you can see, we calculated the initial and final momentums in terms of the velocities. Then we calculated the change in velocity and the change in momentum. Then we calculated dp dt by taking the change of the time and the change of momentum. And then we know that dp dt is equal to net force. Then we applied that to the FNet parallel and perpendicular equations to find out how much force was acting on the body perpendicularly, and then that was plugged into the universal gravitation formula to calculate what the mass of the black hole was. As you can see, the sun orbits the black hole and the program spits out values for the black hole's mass. To find the mass of the black hole, we took the average of all the computationally predicted values of the black hole's mass. Code part 2, as you can see, there is what the speed for the ship was initially in the x direction, and what the speed for the ship was initially in the y direction. Then we found the force of gravity acting on the ship and moon, and then used Newton's second law to plug these forces into the velocity and position update formula for both the moon and the ship to see how the ship and the moon moved in this system. And here's the code output for this. As you can see, while the ship's trajectory is not a figure eight, it did say in the instructions it did not have to be a figure eight. It just needed to be affected by the gravity of the planet and the gravity of the moon, which the ship was. And you might not be able to see that very clearly in this photo, but if you want to see that better, I did put links to my GlowScript code at the end, and you can look it up. Discussion. Similarities and differences. There are no similarities and differences because everything we did was computational, so we can't compare it to any experiment because there is none. Possible sources of error. The coding could be wrong, but I doubt this is the case as the program ran well, and potentially the computer could have read the code wrong, but I highly, highly doubt that. Findings and conclusions. After taking the average of the black hole's calculated mass at every time interval, the mass of the black hole was calculated to be about 1.2 times 10 to the 24th kilograms. If the ship is launched from the moon with an initial velocity of negative 4,850 in the x direction and 43,747 in the y direction, meters per second, the ship's path will be affected by the gravity of both the moon and the planet. And I didn't point it out earlier, but if you look at the GlowScript code, the ship did not crash either. What does it mean? Feel free to go back and review the question in the rubric. The net and its parallel and perpendicular components and the rate of change of momentum in its parallel and perpendicular components, while equal as detailed through Newton's second law, describe two different things. Net force is the vector sum of all individual forces acting on the system, and the rate of change of momentum is the measurement of how quickly and in what direction the momentum vector of a system changes. The parallel components of the two are the component of their vectors that is parallel or antiparallel to the momentum of the system, and the perpendicular component of the two are the component of their vectors that is perpendicular to the momentum in the direction of the center of the turning circle. What if? If we wanted to predict the motion of the entire system, we would need to include potential energy, the work equation, the energy principle, and the kinetic energy equation, along with what was included in this computational model. The force of gravity by the black hole would be a dominant interaction as all the bodies would revolve around it. Here's my GlowScript links